Well, my name's Andrew Joy, and welcome to my talk, Network Prediction Replication's Crystal Ball. Just quickly, a little bit about me. I've been in the games industry about 18 years and using Unreal Engine for about 11 of those years. I mostly do contract work, so the work tends to vary a lot, and I've kind of touched on a lot of systems in my time. But I also work on an open world survival game, which, given the genre, touches on a lot of systems. So I've become a bit of like a programming generalist by force. But every time I come back to Unreal Fest, I seem to be giving a talk on replication, and today will be no different because today's concept is network prediction and reconciliation. So what do I mean by that? Well, I'm going to illustrate with this timeline here. Up the very top, we have client network events, and down the bottom, we will have server network events. And let's just focus on the network part for now. So Unreal Engine uses a pretty standard server authoritative replication model, meaning that if you want to make changes to the server authoritative state, you have to request that on the server and then wait for the change to be made. So for example, if our client wants to fire a gun, they will have to fire the gun and then request that from the server. That can take an arbitrary amount of time to reach the server based on network conditions. Then the server will potentially spawn the bullet and then replicate the bullet back to each client. This introduces quite a lot of round trip time, and this is lag, as you know it, in video games. And the way around it is using a system called network prediction. With network prediction, we aim to immediately cosmetically simulate client inputs on client side as they happen to try and mask this lag. So for example, we would immediately spawn a bullet. We would still need to communicate with the server to change the authoritative game state and to spawn the bullet on every other client, but for our purposes, it's as if we don't have lag at all. It's kind of magic. However, it opens us up to a couple of problems. So if we just look at the client firing the gun and spawning the bullet, what happens if at the same time they get stunned? Maybe another player comes in, throws a stun grenade, very sneaky, and they can no longer fire their gun. They won't actually know that they got stunned until that is communicated back to them an arbitrary amount of time later, and they will still go ahead and fire the gun and spawn the bullet, thinking that they can. When that message hits the server will say, you can't fire a gun while you're stunned, and discard it. So these red events just won't happen. At this point, we have desync. So the client has a bullet traveling along through space, the server has no bullet, and every other client also has no bullet. The way to fix this is with reconciliation, so pretty much correction or adjustment for our mistakes. In this case, the server would have to bounce back a response and say, no, you can't fire the bullet. Go ahead and undo it. So we would roll back the bullet by immediately destroying it, undoing all of its visual and audio effects, and trying to pretend that it never happened. Obviously, the client would still see it for a moment. We can't actually roll back time, but for all intents and purposes, we have fixed our desync. This is still, even though the client may notice it, it's still very preferable to just not having network prediction at all. It's kind of required. So, quick takeaways for today's talk. I just very briefly covered general network prediction concepts. Next, I'm going to talk about how the Unreal Engine implements network prediction for you to use in your own game or other project. After this point, I hope that you'll have kind of a basic understanding of how it all fits together. But from there, we're going to move over and look at the mover component, because the mover component implements network prediction, but enhances upon it in ways that will hopefully give you an advanced understanding of Unreal Engine's default network prediction. Also, the mover component is really cool, and I kind of want to sell it a little bit, but I promise it's mostly about network prediction. And then finally, I'm going to talk about how my own game, Planetation, uses both of these, and some pitfalls that you will probably run into when you first begin on this journey. So first, how Unreal Engine uses network prediction. There's 3 flavors of network prediction in the engine. The first is GAS, Game Playability System, has its own built-in network prediction. It's really good, but if you want to step outside of GAS, it makes it pretty difficult to kind of use GAS's network prediction. Next is the CMC, the character movement component, and this also has built-in network prediction. But again, the moment you step outside of the CMC and GAS, you're on your own. It's very hard to use their network prediction. Finally, we have the NPP, and this is the topic of today's talk, the network prediction plugin. This is a generic base layer of network prediction that you can use to integrate into your own project for your own purposes. But you might be wondering, why don't the CMC and GAS use the NPP? The reason is just they're all very old entrenched systems and they're very hard to move at this point. But thankfully, there is a new kid on the block, the mover component, which is hopefully going to end up replacing the CMC, fingers crossed, because it is awesome and it is built on top of the NPP. There is no gas replacement, which is fine because gas is awesome, but this might be a use case for you if you have your own action system or any number of other systems. We use the NPP internally for a bunch of purposes. So how does the NPP work? Well, if we look at our earlier example, we were doing everything on the game tick, which means everything is dictated by the frame rate. We sometimes might be doing things 12 milliseconds apart, then 20, then 100 if there's a hitch. And furthermore, the client and the server and every other client will have a different frame rate. This makes it very unpredictable, trying to determine when things will happen and sometimes even the order that they will happen. So the NPP, the first thing it does is you move to a fixed tick system, meaning there is a predictable, configurable time in between its state changes. In this case, 50 milliseconds, but it's actually a lot shorter than that, and it's also configurable. So in this case, we would fire the gun for demonstrative purposes. We'd spawn the bullet on the next frame, on the next fixed tick, but we can go a step further than this, and we can actually use numbered prediction frames, indexed prediction frames. And the idea here is we're now firing the gun on frame 100, and then spawning the bullet on frame 101. This makes it really easy to determine, okay, something's going to happen in 3 frames time, or something happened 3 frames ago. But even more importantly, it lets us stagger our server's prediction frames, like you can see up here in the example. So then, as we fire the gun on client side on frame 100, we are also firing the gun on server side on frame 100. Now we have a matching history between client and server. And this makes it way easier to determine if we are out of sync and how we are going to reconcile that mistake. Speaking of reconciles, how do we add that to a fixed tick system? Well, if we take our earlier rollback and snap all of the events to the fixed tick, we've moved everything except the green stunned event on client side. The blue stunned event on server side has been added to frame 99, but where do we put the client stunned event when it receives it? We would roll back and inject it back into frame 99, and then when we replay our history, we determine we couldn't actually fire that gun. We still have to do the same technical rollback of the bullet, destroying it and undoing all of its side effects, but the major difference now is our history has also been updated to match the server. Our history now is as if we had never fired the gun or spawned the bullet in the first place. And this is very important. So you can turn on the network prediction plugin, but I would also very much suggest looking at the network prediction extras plugin. It comes with a whole heap of example source code, but also some test maps. It's super awesome, and we will be drawing from that on the following slides. Speaking of that, I want to warn people now, I'm sorry, but there is a lot of code on the coming slides. The NPP is a very complicated system built in C++, and it uses a lot of templates, and it's just very big. So I'm going to do my best, but yeah, if you don't follow along every single line of code, that's completely fine. The idea, again, is that you will leave this section with a basic understanding of how things fit together, and you'll have a head start when you do it yourself. You'll be like, I know where this goes, I know how to use this, I know how to find that. So, without further ado, the 5 most important types in the NPP. The first is the network prediction component, which is kind of a quality of life system in this case. It does all of our initialization and running through the simulation, but the real workhorse is actually the network prediction proxy stored on the component. If you can't use the component, you can technically just use the proxy. You would just need to do a little bit more manual work. If we look at the source code, you can see that the network prediction component is abstract, meaning you have to subclass your own before you use it, and it is also an actor component. This might be one of the reasons why you can't use it yourself and would want to just use the proxy. The proxy is stored here as a replicated U property, meaning that the authoritative prediction state will be replicated down to each client, and there are other ways that the client can modify this prediction system itself. If we look now at the next types, you might notice that even though they're important enough for me to mention here, they don't have standard names. And that's because the input command, the sync state, and the awk state are types that you will be writing yourself and injecting into the proxy via some template magic. I'll get back to what they do in a moment, but first, they actually make up each of our numbered prediction frames. So if we go back in time and look at frame 98, for example, we will know which input command generated this frame and what sync state and awk state describe this generated frame. Every single prediction frame has one of each. We'll look now at the mock network simulation header file. This is inside of the Network Prediction Extras plugin. And if we look here, it provides a very simple prediction example that just increases a float over time or decreases it. It's a lot less complicated than like a movement system, foreshadowing. But let's have a little look at the input command. So the input command you can think of as the data that the client can modify in order to influence the prediction system. So this is, again, client modified data. The mock input command here contains a single float, the input value, and that just determines how much to increase the total float value by over time. Importantly, it also contains two functions, the net serialize function, which is required for replication purposes, and the toString function, which is required for debugging. All three of our types, the input command, the sync state, and the awk state, require these two functions, so you will be seeing them a lot. Also, by the way, I'll be giving out the code slide, all of these slides at the end, so no stress about like taking photos, feel free, but yeah, it will come back, I promise. Let's look at the sync state. So the sync state is pretty much the current state of the simulation. The client and the server will be modifying this over time in parallel, doing their best to keep them in sync, but if the client detects that it has desynced from the server, it will reconcile its state to match the server. This mock sync state contains, again, just a single float, the total value that we have accumulated over time to this point of the simulation. Again, it contains net serialize and toString, we'll be seeing them a lot, and it adds should reconcile. This function determines whether or not there has been a desync and a reconcile should happen, and then the interpolate function that it also adds controls how it brings the client back into sync with the server. You might remember that the earlier example of rolling back the bullet was a single frame. You destroy the bullet, you undo its effects immediately. That's not technically required, even though you can do it here. Generally, we want to interpolate back to our server sync state, so then the player is less likely to notice that we made a mistake in the first place. We always want to kind of smooth it out. Last, we're going to look at the awk state, or the auxiliary state. This is a bit harder to get your head around, but you can kind of understand it as a sync state that contains data that rarely needs reconciling. It's kind of an optimization. The idea is whenever a reconcile happens, the more data we have to reconcile, the more work we have to do. And in this case, it contains a single float multiplier on how much input is being added to our simulation. In a movement example, for example, this might contain your maximum movement speed. Again, a value that must be kept in sync, but shouldn't really be changing often. It also has the net serialize and toString function that we saw, as well as should reconcile and interpolate, because it is very similar to a sync state. Now that we have those three types, all these 5 types, I have to tell you that I lied. There is actually a 6th type, the simulation type, and let me explain how this one works. All that it contains is a single function simulation tick. It contains no properties, it doesn't inherit from anything, and all this does is generate our new prediction frames. In this mock example, we set our new sync total value to the old sync total value plus our input value, multiplied by our auxiliary multiplier, and finally scaled by delta time. Even though this is a fixed tick simulation and we can hard code this, the interval is actually completely configurable, so you should always manually calculate it like this. So we now have our prediction frames getting generated, but I lied again, there is one more type, and it is the prediction model definition. The only job of the prediction model definition is to tell the proxy about all of our other custom types. I promise this is the last type. This is how it does it. It begins by inheriting from network prediction model definition. You might notice the first time we have inherited from another type. And it has to define 3 types to tell the proxy about. In this case, it's the simulation type. This type only provides the simulation tick function that we just saw to generate new prediction frames. Also the state types, which just tells the simulation about our input command, our sync state, and our awk state. And finally, our driver type, which if you remember earlier, we have to subclass the prediction component, and this is just our custom prediction component. If we look at that now, the prediction component does nothing else except store our simulation object, the object on which we're running simulation tick. Inside of initialize network prediction proxy, that's where we set everything up. And again, we don't have to do much setup. We just create our simulation object and we initialize our prediction proxy. At this point, since we're passing in our model definition as a template parameter, it knows about all of our custom types. It kicks off, it runs through without us doing any more work, and it just simulates our program. So quickly to recap that, because it was a lot, there are 7 important types in the MPP. The network prediction component and proxy, which do all of the running of the simulation. The input command, sync state, and the awk state, which compose our prediction frames. The simulation type, which is responsible for generating new prediction frames. And finally, the model definition, which tells our system about all of our custom types. But something here is missing, and that is what actually calls this simulation tick function. This type doesn't inherit from anything. This is not a virtual override. This is called as a template concept. So I won't go too deep into what those are. You can think of them as requirements on certain types that we're passing into our template system. But in this case, our network model definition simulation type is required to have a simulation tick function with that exact name and taking the exact parameters that we just saw. If you pass in a different type, it will fail to compile. Same for our state types, which have the net serialized toString and sometimes should reconcile and interpolate in the case of sync state and awk state. And finally, what does the driver type require, our custom prediction component? Well, this one's a little bit special. These are the 4 template concept functions that the mock example provides, but there's actually 7 template concept functions that the driver type can have. Each of these are also technically optional. So, for example, produce input is where you produce new input commands. If you omit this function from your driver type, from your custom prediction component, the simulation is actually smart enough not to fail to compile, but it will just bypass that part of its own prediction system and not use input if you have, like a fully predictable prediction system or whatnot. This part starts to get pretty complicated, so if you want to know more, I would say go to the network prediction driver header file, and specifically the line numbers I have commented beside each one. Whoops, that one's on the wrong line. And you can see more about both how they're used and the parameters that they are expected to have. So let's move on. At this point, I hope you have a rough understanding of how the NPP functions, but now I want to enhance that. I want to give you a more advanced understanding. And the best way to do that is with the mover component. So let me give you a very quick example. This is potentially the world's worst demo, but it breaks up the code slides, so it's worthwhile. This is just jumping into my own game in a version that we can just run around in. I want to point out how we're using the mover component. You can walk, obviously, you can sprint, but you can also fly a jetpack, and if I wait for my energy to come back, you can also dash around. So this is running with lag simulation, 150 milliseconds, and it still feels really good. That's because we're leveraging both the mover component and the network prediction system under the hood. Stuff that up at the end. Okay, so let's move on. This is how you turn on the mover component. Note that there is also a mover examples plugin alongside it, which contains, again, a whole bunch of example source code and test maps, and it's a great place to learn. And deja vu, but we're going to be drawing on that for the next couple of slides. So this is the mover component in the source code. It is an actor component, you might notice. So how does it use the network prediction system? The network prediction system is actually injected here as a backend class. And the backend class basically runs through the lowest level of the movement system. It runs it for us. The backend class has to be a mover backend liaison interface. And if we look, there are 3 mover backend liaison interfaces in the source code at the moment, as of 5.5. The first is the network physics liaison, which gives us basically physics-driven multiplayer movement if we're using the mover. The last is the standalone liaison. If we know that we're making a single-player game, we would use this just then we're not paying the overhead of multiplayer movement. But by default, the mover system uses the network prediction liaison component. And if we look at that now, it is just a network prediction component and a mover backend liaison interface. It has these 5 template concept functions, and if we quickly go back to the mover component, you will see that it also has the same template concept functions, except in this case, they're not template concepts. This is because the mover component began life in the Network Prediction Extras plugin as the character motion component. It is heavily designed alongside the network prediction system, and it mirrors it in a lot of ways. It uses a fixed tick for movement, and it uses a lot of the same functions and state types in order to run through its simulation. It now exists as the mover component in the mover plugin, but you can still see that old version back in the extras plugin. If we go back now to our prediction liaison component, we'll see the first improvement that the mover does when using the MPP, and that is the simulation tick function is now on the custom prediction component. This is, again, the first improvement. It does away entirely with this separate simulation type, so if that confused you in the previous set of slides, good, because the mover system simplifies it by killing it off. If we look at the mover model definition, this is how it does it. It just provides the custom prediction component as both the simulation type and the driver type, and that works just fine. But what about the state types, the input command, sync state, and awk state? Well, this is actually another improvement that the mover component does. It does away entirely with the awk state. I mentioned that it's kind of a bit hard to get your head around, and that's because it's mostly a performance optimization. The mover system, it's not only very complicated, so it needs simplicity, but it also just doesn't need that performance improvement. So instead, it just doesn't use the awk state, purely input and sync state. It still needs to provide an awk state, so if you also want to cut it from your own simulation, then you would just provide a dummy awk state like the mover does that will never reconcile and contains no data. So again, no awk state. Let's look now at the input command, and this is another improvement that you could potentially look at using yourself. The mover input command contains nothing apart from this mover data collection. The mover data collection is initialized here with a character default inputs type, but you can think of it like a tmap of instanced structs. This is very important because the mover component is trying to improve upon the CMC, and the CMC tries to do everything. It has flying, swimming, crouching. It's one huge monolithic component, so it's very powerful, but it contains a lot of stuff that you probably won't need. The mover component, instead of doing everything, tries to do anything, meaning it knows that each game is going to have its own kind of flavor on its movement system, and it lets you add your own data to the input command. This just naturally works both with the movement system, but also it naturally works with the prediction system. In this case, you can just add structs and then retrieve them by their type and use the data contained within. If we look quickly at the character default input struct, we will see that it just contains the most generic movement inputs possible. What direction we want to go, what direction we want to face. Even this ability to jump, there's comments in the mover plugin, is this too specific? Should we remove it? So it might even be gone in the future. I just want to reinforce that this is stored inside of the input command, but you can kind of think of it like the default input command, plus whatever else you want to store inside of it. If we look now at the sync state, we'll see that it contains the bare minimum data required for the mover simulation to run, things like movement mode, layered moves, movement modifier, but also it just contains a mover data collection again. This mover data collection is initialized with a mover default sync state, so you have this already provided for you. And this mover default sync state just contains the bare minimum sync state you would expect for any movement system, your current location, rotation, velocity, etc. Again, it's stored inside of the sync state, but you can think of it as the default sync state. And again, they're also stored inside of mover data collections. So that means that you can store any data you want in these, right? If you want to add your own movement data. Well, that is true, but it needs to inherit from this type, the mover data struct base. And if we look at that now, you'll see something very familiar. The mover data struct base has a net serialize and a toString function, just like our other types, as well as should reconcile and interpolate. This is how it just kind of magically works inside of the MPP, as well as the networked physics movement and, technically the standalone liaison as well. Additionally, it exposes get script struct and clone just to treat it a little bit more like UObjects. You don't need to worry about that. But importantly, it also has an add referenced objects function. And that's because even though all of these types are ustructs, they're not actually stored inside of a uProperty. So if you need to hold a reference on one of these to a uObject, which we will see on a coming slide, foreshadowing, you need to manually reference it here with add referenced objects. Otherwise, it'll get garbage collected. Okay, to quickly recap, we have all of these types on the movement system. We do away immediately with the simulation and the awk state, and we are just using the input command, which stores a character default inputs, and the sync state, which stores a mover default input state. This explains how it works, but something is still missing, and that is how do we actually populate our input command and our sync state in a mover context. So I mentioned that the mover uses the prediction system as a backend. Normally on a prediction system, you would use the produce input function that I mentioned earlier to generate your input command. That's a little bit out of the way though for a movement system. So instead, as a backend component, it will call the matching function on the front-end component, on the mover component. And even this is a bit out of the way. In turn, the mover component will call that same function on the owning actor. So you can set up all your movement input ready for network prediction directly on the actor that's using the movement component. It calls it via this interface, mover input producer interface. And if we look quickly at the mover examples character, I just want to first point out that this is actually a pawn, which I find very hilarious, but also it further reinforces that we're moving away from the CMC and also the character, which is very tightly coupled with the CMC. We no longer need that for our simulation. It is also a mover input producer interface, which provides the produce input function. And if we look quickly at that now, this is how you would set up your movement input command. You pull the writable character default inputs out of the collection. You set whatever values you want on it. This function is very big. And then you have a valid input command for your prediction system. So that's the input command. What about the sync state? Where do we generate that? Well, again, if we look at the default prediction component, it would normally be done on in the simulation tick function. That is out of the way. So instead, as a backend component, it calls that on the mover component. But this time, instead of calling simulation tick on the owning actor, which doesn't really make sense, you can actually tell the mover component what movement modes you want it to be able to use. You can tell it, I want you to be able to walk, I want you to be able to fly, but don't worry about swimming. So it might only have two movement modes, say walking and flying. The mover component knows which mode is currently in use and would call simulation tick on that specific movement component, on that specific movement mode. If we look quickly at movement modes, we can see that the walking mode is a base movement mode and it provides this simulation tick function. In order to use this movement mode, we would queue it, because again, we are in a fixed tick system. We can't make changes outside of that unless we want to accidentally cause a reconcile. So we tell it instead, on the next fixed tick, please go ahead and change our movement mode. I just want to quickly point out as well, there are plenty of other alternatives to movement modes. The mover component is incredibly flexible. But if we are using a walking movement mode, this is how we would generate our sync state. We would pull out a read-only version of our default inputs, the one that we just generated on the actor, and then a writable version of our default sync state. We then set all the values, again, a really big function, but at the end of it, we have a valid sync state and therefore a valid prediction frame because we also have the input command. So that's it, it just kind of works. I hope that that kind of illustrates some advantages that you could pull from the mover component yourself if you even just don't decide to use the movement component. But now I want to quickly talk through some pitfalls that you might run into in the course of integrating this into your own project, using my own project, Planetation. To begin with, it actually crashes, and that is because there is a native-only crash in the mover component. What do I mean by that? So if we were to spawn this mover examples character actor, this is just a native class, right? It's not a blueprint. It has a movement component, and spawning this actor would cause your game to crash. If, however, you blueprint that type, so you inherit it but you do no other work, it will spawn naturally and not crash at all. That's because the mover component requires a call here to refresh shared settings before any ticking happens. And currently, that is called in these 5 functions, but all of these are blueprint-only code parts. In order to fix this, it's actually pretty easy. You would just make your own mover component, which you probably want to do anyway because it gives you a lot more control. In this case, we inherit from the character mover component, which is kind of a CMC-like specialization of the mover. And inside of onRegister, just to make sure it happens before tick, we check if we're a blueprint because we don't want to do this work twice, and then we manually refresh our shared settings. We have fixed the native-only crash. Next, I want to talk about short-lived prediction systems. So you might have noticed earlier when I was running around, it was actually important. When I was using the Jetpack, we were burning through an energy resource on our screen, and I had to wait to be able to dash again. In our game, that is a resource, like I just mentioned, and resources are a predicted system. It doesn't have to just be actions and movement, it can be anything. So we don't want to always be running a resource prediction system because really resources only change rarely, right? It's not like a movement system which, probably changes all the time. Instead, we want to be able to turn it on when we're draining our resource or replenishing our resource, and then turn it off again until we decide to use that resource next. You might think, oh, I can just turn off the tick on your custom prediction component, right? And that would stop the proxy ticking. That's not actually true. And I need to apologize again because I did lie. There is one more type, the Network Prediction World Manager. And the World Manager is responsible for batching every network prediction component in your world and then calling them all on the exact same fixed tick. If you have a lot of prediction components, it's going to do them all on the exact same fixed tick, and this is why you might want a short-lived system. If we go back now to that initialized network prediction proxy function where we set everything up, and look again at this init function where we pass in the model definition, this is, all that this really does is call this function, register instance, over here on that world manager. I just want to quickly point out this world manager is a world subsystem, so it's kind of global, but not really. But also there is this other function, unregister instance. You can just, if you want a short-lived system, you can do what we do and just manually call register instance and unregister instance to give yourself complete control over the life cycle of these systems, just as an optimization. Next, I want to talk quickly about non-replicated movement bases. So first, what is a movement base? Because maybe not everyone is aware. Let's say that we have this cool platform, and then we put a cool character on top of it, and then this cool platform wants to move. Maybe it's a spaceship we're standing on top of, or a helicopter we're inside of, or even just a magical platform that roams about. If it moves, one of two things will happen to our character. If we're using unbased movement, the character will be left behind and eventually fall off when the platform moves out from under it. But if we're using based movement, the character will move with it and then perform its movement in addition to the platform's movement afterwards. There is a problem here though. The movement base in the mover component is stored inside of the mover default sync state, and this entire sync state needs to be able to replicate. So if we are standing on top of a base that cannot replicate, then we will see based movement on our end, and everyone else will see unbased movement because there is no reference to whatever base we're standing on. We end up with movement desync. This generally is easy to fix for probably most people's games in this room. You can either turn off based movement entirely, or you can just make sure that everything you can stand on is a replicated actor. But we have a kind of special use case. We use the voxel plugin, which is amazing, but it basically generates a huge complex environment for us underneath our feet. We do generally want to use that as a movement base, but it's too complicated to replicate. So instead, each client will also generate the exact same landscape, again, non-replicating. And using determinism, they just kind of match up. That causes problems with our movement base, and the voxel plugin does have a solution for this. If you're using the CMC, it has a method to rebase your movement over instead to this one replicated world actor, which fixes everything. Unfortunately, that's a little bit harder to do in the mover plugin. The way that we solved it is manually rebasing it in this on-post movement event on the movement component. I won't go into depth about how that works because it's probably not relevant to everyone in the room, but I do want to point this out because A, if it is relevant, please come get me, I'm happy to give you the code. But B, if you have any movement, any adjustments you want to make to your movement system, this is where you would do it after the movement sync state has been finalized. Finally, I want to talk about debugging because you will break things and you will break things hard. In our case, we make sure that we always play as a lag simulated client, just what you saw earlier. So we turn on network emulation in the editor settings. If anyone's not familiar with this, it just adds artificial latency and packet loss to your multiplayer play and editor sessions. You can find it in level editor play, which again is in the editor settings, not the project settings. So this will affect every project you're making with this version of the editor. We also make sure that we always play as client. which means that it will spin up a dedicated server for us in the background and connect us to it, and therefore we're always playing as a lag simulated client. This makes it really obvious whenever there's issues with our prediction simulation, but also just helps you find a whole heap of multiplayer bugs. If you want something network prediction plugin related, these are the console commands that it exposes. The most useful to us has been print reconciles. And what this does is whenever a reconcile happens, it will take your entire state and dump all of the data that it can using those toString functions we saw earlier to your output log. This is very preferable, at least to us, over debugging with breakpoints because that naturally breaks up your simulation. And then you can just kind of go through afterwards and find all of your reconciles and what caused them. Makes it really easy to just cut out as many reconciles as possible. So to recap, I've gone very quick. I talked through the general concept of network prediction from a high level, and then I talked about how the Unreal Engine implements it and provides it to you in the NPP. That hopefully gave you a basic understanding, but then talking about the mover component, I hope also gave you a little bit of a more advanced understanding from their use case. Also, hopefully sold you a little bit on the mover component. Finally, I talked about some potential pitfalls you might run into using both of these inside of our in-game Planetation. And that is it. Thank you very much for sitting through all of the code. Let's maybe go to questions. That's all of the slides in case you do want those code slides.
If there's any questions.
Great talk. Thank you so much.
Thank you.
Did you transition from the CMC to the mover component on the game you're working on? And if you did, what was that like?
On the what, sorry?
On the game you're currently working on, did you transition from CMC? And what was that process like, transitioning your code base from a CMC network movement to the mover component movement?
So it was actually just an all-around improvement because previously, one of the issues with the CMC, maybe someone else has managed to address this in their own use case. One of the issues with the CMC is that it doesn't do client predicted movement very well. We ended up using a marketplace plugin, the client predicted movement plugin, which basically replaced the CMC with a custom version that was kind of hacked together to give you client predicted movement. Without that, it felt kind of very slow on our end playing the game. Moving to the mover component, we kind of managed to do away with all of that. It just kind of works out of the box. It also gives you a lot of other benefits. So one of the main ones is if anyone's kind of like launched an actor, like launched a character before, that can usually cause skips, like reconciles on your end if you're using the CMC. Using the mover component makes it super easy to just like fling your character around and it just works. Even if you're first person inside of that character, it feels really smooth. Yeah, I hope that answers the question.
Great talk. Do you have any advice you can give people as you've been using this, I assume in other instances of your game, of any architectural advice for dealing with rolling back prediction or anything like that, just in general that you've found while using it?
Yeah, so one of the bigger things, I guess, is you want to try and do anything that's related to each other in the same prediction system. So if you have like your own action system that uses resources, if you have that as two different systems, so resources simulated and actions simulated, they don't really work too well together, just like, you know, using gas with a CMC, like it's not necessarily designed to just work together. So in our case, we do have a custom action system to an extent, and yeah, we use them both in the same CMC. I would say as well, just be very careful not to store too much data in it as well, because whenever like all of this stuff gets transmitted regularly over the network, it does add some bandwidth. And if you have a lot of actors in your game all doing this, you'll choke out the network. Yeah.
Awesome talk. Just on that, is there any issues with using gas and the MPP, or is that can you use those together?
Yeah, you can use this with gas. Just as always, if you're like moving between, if you're kind of cooperating between two prediction systems, especially two that are written in completely different architectures like this, yeah, just be very careful because it tends to cause a lot of reconciles. You kind of want like a little buffer between them. We don't use gas for everything, so I would say we haven't run into any problems, but someone else that uses gas more extensively might run into some problems. Yeah, we haven't had any problems though. Thank you.